In mathematical modeling, close numerical alignments often trick the eye. Two complex data structures can converge so tightly that they appear to be governed by the exact same underlying law, but microscopic inspection reveals a gap. Take two specific empirical data points extracted from a monitored system. We have variable A measuring 96.4 and variable B measuring 57.2. This animation shows the missing exponent transform applied to these numbers. We divide A by B and square the resulting ratio. The output is a highly specific decimal, approximately 2.8402. On the left side of the screen is an exact mathematical constant, alpha plus 1, which equals 2.8392. Compare the two sides. The empirical ratio on the right hits the constant on the left with a residual margin of error of less than 1/1000th. When analysts see a convergence this tight, the immediate assumption is that the empirical ratio is directly governed by the structural law of alpha plus 1. The error is written off as standard statistical noise. We're going to dismantle that assumption. By building the exact mathematics of the 2-phi continuous sieve and the Tribonacci shear, we will prove that this empirical ratio is a monitored shadow, constrained by finite measurements, and permanently isolated from the true theorem. To understand the actual mechanics at play, we need a rigorous method to map a continuous random variable onto a discrete set of sequence steps. This diagram illustrates a continuous uniform distribution, denoted as U. It represents a random variable that has an equal probability of landing anywhere on this line between 0 and exactly 1. We introduce a scaling factor, lambda, to multiply the length of the line. Then we apply a FLOW function, a mathematical operation that rounds any value down to the nearest whole integer. The rigid vertical lines drop down to chop the continuum into discrete standardized bins. We call this the random index hinge. Notice how the shaded standard bins share the exact same area. Because the initial distribution was uniform, the probability weight of landing in any one of these complete bins is exactly 1 over lambda. But the sequence does not end cleanly. The final bin is truncated. It carries a distinct, smaller probability weight, a tail weight, calculated precisely as lambda minus the integer m divided by lambda. This mathematical hinge creates a rigorously controlled environment. We can now uniquely weight the outcomes of any discrete sequence using a single continuous random draw. We apply this hinge to a specific numerical sequence, the Tribonacci window. The Tribonacci sequence operates by adding the previous 3 terms together to generate the next one. We will use the specific window of 24, 44, 81, and 149. Here we have 4 distinct sequential blocks. The bracket grouping the first 3 values shows the order 3 additive condition. 24 plus 44 plus 81 equals exactly 149. Now we overlay our continuous probability slider from the previous model onto these 4 discrete blocks. We lock the total length of the slider, the lambda scalar, precisely to 2 phi, which is 2 times the golden ratio. Setting lambda to 2 phi triggers a mathematical collapse. The messy tail weight formula for the final block algebraically simplifies, allowing us to calculate the exact expected value, the theoretical average outcome of this random variable.
The final expectation collapses perfectly to 149 over phi squared. You might compare this expected value to a standard unbiased average of the 5-point Tribonacci sequence, which is exactly 114.4. If you take the sieve expectation of roughly 56.91 and double it, you get 113.82. Doubling the expectation does not recover the standard mean. The value of 149 over 5 squared stands entirely on its own. It is an exact mathematical expectation derived from the golden ratio, cleanly separated from the noise of standard empirical averages. To fully secure this system, we have to isolate the fundamental constant that anchors the entire Tribonacci sequence, alpha. On screen is a Cartesian plot of the cubic polynomial x cubed minus x squared minus x minus 1. Alpha is defined mathematically as the unique real root of this polynomial that intercepts the x-axis between 1 and 2. If we take that polynomial equation set to 0 and rearrange the terms across the equal sign, the geometry cleanly resolves. Alpha cubed minus alpha squared equals alpha plus 1. This shear identity is an exact mathematical theorem. It is derived entirely from the polynomial structure.
independent of any empirical measurement or interpretive language. This stark typographic statement confirms a crucial mathematical property. By applying the rational root theorem, we find no integer fractions satisfy the equation. Therefore, alpha is strictly irrational. It cannot be expressed as a simple fraction of two whole numbers. Its decimal expansion is infinite and non-repeating. Any exact system built on alpha inherits this rigorous irrationality. It establishes an unyielding boundary between absolute mathematical law and finite measured data. We now have the tools to evaluate our original empirical data. We must place the exact irrational mathematical constructs of alpha plus 1 and 149 over 5 squared into direct collision with our starting variables. Bringing back our split screen, the left side is locked to our proven exact irrational identities. On the right side, we stop treating 96.4 and 57.2 as decimals and expand them into their exact fractional equivalents, 482 over 5 and 286 over 5. When we square the ratio of these exact fractions, the output is forced to be strictly rational. The result is the massive fraction 58,081 over 20,449. Because alpha is a proven irrational, alpha plus 1 is also irrational. This creates a hard mathematical boundary. A rational fraction, regardless of its precision, can never equal an irrational number. The continuous 2-phi sieve and the Tribonacci shear identity represent the exact mathematical core of the system. The empirical alignment is a monitored numerical hit, a rational value that tracks the theorem without merging with it. This fluid simulation demonstrates the reality of high-level modeling. In strict mathematics, incredibly close numerical convergence is never a substitute for structural proof. The two sets of values can press up against each other infinitely, conforming to the exact same shape, but the barrier remains. Separating the irrational theorem from the rational shadow ensures theoretical rigor. This distinction identifies the exact mathematics while acknowledging the limits of numerical resonance.